Hey guys, welcome to problem 4 and problem 5 of the AMC 2024 10B. So I think if you're coming from the previous video where we knocked out 1 through 3, I think problems 4 and 5 are personally much more difficult. But then I think once you get over these problems 4 and 5, the next 3, 6, 7, 8 again become easier. So I guess let's just dive right into it. So problem 4, balls numbered 1 through 3 are deposited in, or 1, 2, 3, ... are deposited into 5 bins labeled A, B, C, D, and E. Ball 1 is deposited in bin A. Then balls 2 and 3 are deposited in bin B, and then the next 3 are deposited in bin C, and so forth. In which bin is ball 2024 deposited? So again, this is a challenging problem, but let's break it down. So what they're telling us is that bin A, bin B, C. Oops, didn't mean to do that. So bin A is going to have balls, ball 1. Bin B is going to have 2, 3. This one's going to have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this bin is going to have 1 ball, this bin is going to have 2 balls, this bin's going to have 3, this bin's going to have 4, and this bin's going to have 5. So this is just to clarify in case, maybe someone didn't understand the question, just to help visualize the question a little bit. So this expression can be modeled in sigma notation. And we actually don't know its upper bounds, but that's what we're going to solve right now. So what does this mean? Well, again, for bin 1, you're only going to have 1 ball. But then for bin 2, right, n is going to go up by 1. And for bin 2, all of a sudden now, you are going to have 2 balls. And then for bin 3, you're going to have 3 balls, and so forth. And you want to get to a point where you reach a sum of 2024. Because once you reach a sum of 2024, you know that's where the last ball is dropped. And then you have to find into what bin that last ball is dropped. So from a previous video, there's a formula we use for this, where this is basically equal to n plus 1 over 2. And since this is just this is kind of solving out the sigma notation. And going back, we want to know when this is equal to 2024. So let's solve it out. Well, then you have n times n plus 1 is equal to 40, 48. And therefore you have that, you would have to do the calculation, maybe play around with some numbers, but I can tell you that n is going to be around 63. And notably, I put this equal to, but technically speaking, n should be less than or equal to. So 63 will give us a value that is less than 48, but if I were to plug in n for 64, then this wouldn't work, as the value would be greater than 4048. So 63 is the last integer that works. Well, let's just try this out to make sure. So if n is 63, it would be 63 times n plus 1, which is 64, over 2 has to be less than 2024. And this is, in fact, 2016. So what do we know now? Well, we know that if you have a row of bins, so if bin A is bin 1, then you have bin B, C, D, E, and so forth. Bin 63 is going to have the 2016th ball. Therefore, we know that bin 64 will have the 2024th ball. This is because it's the next since we didn't quite reach 2024 in bin 63, we know we are going to reach that number in the subsequent bin. So now the last question is, to solve the problem is, well, which letter corresponds to bin 64? And for that, you would just divide 64 by 5 and see its remainder. So 64 would have a remainder of 4. So basically, we do each of these cycles 12 times, since 12 times 5 is 60, and then you would have 4 bins left over. So it would be 1, 2, 3, 4. So this bin right over here would be the 64th bin. So the answer would be bin D, which is conveniently also option D. All right, on to problem 5. In the following, what did I do? In the following expression, Melanie changed some of the plus signs to minus signs. And here again, we have just a series, just a large summation of notably odd numbers. When the new expression was evaluated, it was negative. What is the least number of plus signs Melanie could change to make the value negative? Well, I think it's helpful to first know what is the sum of this expression. Well, interestingly, we can add 1 plus 99 to get 100, 3 plus 97 to get 100, 5 plus 95 to get 100. And what I'm doing here is I'm basically grouping up the largest value of the smallest value, and then the second largest value of the second smallest value, and so forth. And we get a bunch of these pairs of 100. And because the expression goes from 1 all the way to 99, but notably it's only the odd numbers. So instead of being 100 numbers, we're only going to have 50. So we have 50 numbers, and we take 2 of each number to make a pair of 100. So we will have 25 pairs of 100. So the sum of the expression would be 2,500. So why did I calculate this? Well, if we know that the total value of the expression is 2,500, well, then we know that the value of the positive numbers has to be less than 1250. This is because if you divide this by 2, you would get 1,250. And we know that if the value of all the positive numbers summed together is less than 1250, well then, for example, maybe it's 1249, then the sum of all the negatives would be 1251, so the total expression would be negative. So this is our next, that's our next hint, that the value of all of the positive numbers has to be less than 1250. So, well, how are we going to calculate specifically how many numbers we have to change? Well, the thing with odd numbers is there is an interesting property when you add them up. So I'm going to give an example. All right, so right here we have n equals 4 because we have, well, obviously 4 odd numbers. And the theorem states that if you have n odd numbers, their sum is just going to be n squared. So 4 squared. And if you would do the math here, like this is 10, this is 6, 16, so that checks out. Similarly, another example is, well, we already found the sum is 2,500, but I also know that there are 50 odd numbers here. So 50 squared should give me 2,500, which it does. So how does this help us? Well, the number of positive odd numbers, or the sum of the positive odd numbers, has to be less than 1250. So now if we just solve for n, and since we want to be most efficient, we want n to be as close as possible to 1250 without obviously being greater than it. And again, you'd have to play around with the numbers, but 35 squared would give you 1,225, and this is the closest you will get to your target value without being greater than it. So now you know that you will have 35 positive odd numbers, and since n is 50, since going back to the original expression, we said that we have 50 odd numbers. If there are 50 odd numbers and 35 of them are positive, well then 15 of them must be negative, which will be our final answer. So the answer will be B15.